So when do we want to use Gauss's law? Well, one, Gauss's law applies only to a closed surface, and we're going to call any closed surface a Gaussian surface. That surface is mathematical in nature. The circle through the integral is a reminder to us that this applies to an enclosing surface. Again, a Gaussian surface is a closed surface through which an electric field passes. It's not a physical surface and doesn't need to correspond with the boundary of any physical object. It is an imaginary mathematical surface in space surrounding one or more charges. Gauss's law is applied in situations where, from symmetry and superposition, the shape of an electric field is known. So for us, whenever we see an electric field that is cylindrically symmetric, we should consider using Gauss's law. Whenever we see an electric field that is spherically symmetric, we should consider using Gauss's law. Whenever we see an electric field that has planar symmetry, we should consider Gauss's law, because in each of these situations, the evaluation of an integral using Gauss's law becomes a trivial matter. We'll see this in the next set of videos. So in talking about Gauss's law, we have to talk about Gaussian surfaces. Now, don't let that fancy phrase fool you. A Gaussian surface can be any surface in space, real or imaginary. The surface doesn't have to describe a real object and needs to be only mathematical in nature. For example, a Gaussian surface can be a sphere. Spheres can be described mathematically. A Gaussian surface can be a cylinder. Those can be described mathematically as well. Gaussian surface can be a cube, which can be described mathematically. And if you like peanuts and can spend the time to define mathematically a peanut, then your Gaussian surface can be a peanut. These don't have to be, though, real surfaces in space. Any surface that you can describe mathematically can be used as a Gaussian surface. And if you can describe that Gaussian surface mathematically, then the amount of charge inside that Gaussian surface can tell you the electric flux across that surface due to the electric field. Now, Gaussian surfaces and using Gauss's law to calculate electric fields is most useful when the surface can be constructed that matches the symmetry of an electric field passing through it. If it does, then you should definitely consider using Gauss's law to simplify the calculation of the electric flux in that region of space. So in talking about symmetry, there are three main types of symmetries that we have with electric fields. We have cylindrical symmetry. Cylindrical symmetry is a symmetry of an electric field that is symmetric, usually about a very long line of charge. That line of charge is so long, it is infinitely long. And what happens in that situation is you get an electric field that is cylindrically symmetric. So I'm drawing a bunch of electric field lines. This is a line of charge. So this line of charge is in three-dimensional space, but being a line, the line only has length. It doesn't have width or depth, just a length. And if this line of charge, let's say, were due to a uniform charge distribution, we would have cylindrical symmetry of the electric field. So what I'm attempting to sketch here is just a three-dimensional perspective of this electric field that has cylindrical symmetry. But let's take a vantage point in which we are looking straight down on this line of charge. As we are looking straight down on that line of charge is going to look like a dot. And your electric field lines are going to be radially away from that dot. Now, here's what we mean by cylindrical symmetry. If you create a cylinder centered on the line of charge, the electric field everywhere on that cylinder will be normal to the surface of that cylinder at that point. So no matter where you are on the surface of the cylinder, the electric field at that point is going to be normal to the surface of the cylinder. And notice for this cylinder, from the electric field lines, the electric field has the same strength, the same magnitude at each of those points. Because of this, no matter where you are on the cylinder, the electric field looks exactly the same. This is what we mean by cylindrical symmetry. The electric field looks the same no matter where you are on the cylinder. So that's one type of symmetry, cylindrical symmetry. Another type of symmetry with our electric field is spherical symmetry. Let us take a point charge. If we take that point charge and look at the electric field that is in the space surrounding that point charge, that electric field is spherically symmetric. What that means is if you were to take a surface, we'll say a Gaussian surface, of a certain radius centered on the charge, the electric field at every point on that surface is normal to the surface. And notice how these electric field lines that are normal to the surface also have the same magnitude at any point on the surface of this sphere. So this is a charge distribution, this point charge, that has spherical symmetry because it looks the same no matter where you are on the sphere. And this is true, this spherical symmetry is true for point charges. It's also true for spheres of charge. Outside the sphere, the electric field has spherical symmetry for any other sphere of a radius r outside of the sphere of charge, and it still has spherical symmetry. It looks the same no matter where you are standing on the sphere. Another common type of symmetry that we have with electric fields is planar symmetry. Planar symmetry is due to an infinite plane of charge. So imagine a sheet. a two-dimensional sheet of charge. This two-dimensional sheet of uniform charge that is infinitely big will generate a uniform electric field that points perpendicularly to the surface of the plane. So these electric field lines, notice, are perpendicular to our plane. Now, if we were to create, let's say, a Gaussian surface that matches this planar symmetry, so let's take two planes that are parallel to this sheet of charge. So the two planes that are parallel, I'll just choose a cylindrical box. So this cylindrical box has a top surface. It passes right through the plane, and it has a bottom surface. The top surface and the bottom surface, the electric field is perpendicular to both of those surfaces. So the electric field is parallel to a vector normal to each of those surfaces. And no matter where you are standing on this surface or on the bottom surface, the electric field has the same magnitude and it has the same orientation relative to that surface. The same thing with on the side, even though an area vector, a vector normal to a point on the side, is perpendicular to the electric field on the side, notice that no matter where you are on the side, the electric field is going to look the same everywhere on that side. This is what planar symmetry looks like.